See here, that was a joke. Anyway, if the pucks are initially 10 meters apart, show that the electrostatic potential energy at this separation is negligible compared with the kinetic energy of a moving puck. So this is not a tricky question at all. We just have to calculate the electrostatic potential energy and the kinetic energy and show that it's negligible. And this is all at 10 meters apart. So the electrostatic potential energy was E equals, that's EP because electrostatic potential, constant times Q1, Q2 divided by R. Remember, it wasn't R squared because it's force times distance to get the work, which is what the potential energy is a measure of, the work done to raise it to that potential. And we have to plug in the numbers and calculate that compared with the kinetic energy of the moving puck. So the kinetic energy, it's an easy one, is half times the mass, which is given to you, 2 grams, half mv squared, 21 meters per second. And when you perform the calculations, you get around 2, and you get around 400 and 440, I think. And we're dealing with, I'm pretty sure it was joules was the order of magnitude, but in either case you can see that the kinetic energy is much, much larger than the potential energy. So the potential energy 2 is 200th, less than 200th, and when you work out the actual values, so these are just approximate, and anything that is more than an order of magnitude out, an order of magnitude is times by 10, so 1 and 10 are 2 different orders of magnitude. 100 times is 2 orders of magnitude out. This is definitely negligible compared to these two. Anyway, D. Let's change colour for D. By considering the kinetic and electrostatic energies, calculate the distance of closest approach. Okay, well, so we're trying to find R at the closest approach. So what's a good way to look at this? We have to consider the energies. Maybe we could come up with an energy equation. We know that the total energy is the kinetic energy of the initial of puck 1, or the red puck, I think. Initial. Okay, this would be an awkward equation, but it's just for the notation's sake. Or awkward notation for the equation's sake. So we've got the kinetic energy in total. That'll equal all the energies. There'll be the kinetic energy, the final of the red puck, plus the kinetic energy of the blue puck, the final. It started with 0, so and then it went to something. So, and let's just make a wee bit more space. We also have to add the electrostatic potential energy at the closest position. Okay, so we may as well, I'll write out this formula and then we can see where it will go, but I'm not going to actually go through the entire process. So the kinetic energy of the red puck, the initial, is going to be half mv. In fact, let's write that in as 0.002 times v was 21. Okay, this is a little bit clumsy, sorry. 21 squared, meters per second squared. We found earlier that the velocity at the closest point is 7 meters per second, so that actually gives us more numbers to put into this. The kinetic energy of the red puck, final, is half times 0.002 times 7 squared, plus the kinetic energy of the blue puck, final, is half times 0.004 this time, times 7 squared. And then the last part, the potential energy at the closest point, was plus the K constant was, I'll just put it as K, you can substitute it in yourself if you're wanting to work through this. K times Q1, well, whether they were both 1.5 times 10 to the minus 6 coulombs. I'm just going to put them in here anyway. Q1, Q2 over R. So you know the constant, you know Q1 and Q2, which are both the same. That means in this whole equation, r is the only unknown, so you can substitute all the numbers in, and there it is, there's the full equation. Substitute all the numbers in, rearrange for r, and then you've got the distance of closest approach. It works out to be about 6.9 centimeters, 6.88 or something like that, 0.0688. But anyway, that's what it is.